And one example of benzene ring, carbon 6, hydrogen 6. The alternating double bond and single bond in the benzene ring there, and you can have two different representations there. Now, abbreviated representation of the resonance structure, instead of drawing the double bond, alternating double bond and single bond there, and you simply put a circle in there. Now, this is one thing I want to point out before you get into organic chemistry. When you draw a benzene ring, it's either alternating double bond or single bond, or a circle within the hexagon ring, not both, okay? And as an organic chemist student, when I see circle and the alternating double bound and single bound, it drives me nuts. And that happens on a regular basis when I have, when I teach organic chemistry, and especially when I collect the lab reports in the labs there, we ask people to write the chemical reaction equation. I always see this. No, don't do that. Okay, this is as bad as it can get. So for organic chemists there, I don't want to see this. So make sure it's either a circle representing the alternating double bound moving around very quickly, or you draw alternating double bound. So it's either a circle or alternating, and never both. All right. So that was the resonance theory. Basically, we showed you that if you have a Lewis structure that contains double bound or triple bound there, the electrons that forms the double bound and triple bound are capable of moving very rapidly between two different positions there. As a result, and you end up with what we call the resonance structure. Another topic we do want to mention as Chem 101 is the prereq for organic chem there. And another situation is that once you draw the Lewis structure there, we still want you to be able to determine the charges. We use the term formal charge on atoms in the Lewis structure there. So now in ionic compounds, the charges are clear. Well, sometimes not so clear with the transition metals involved in there, but at least we know metals will be positively charged, non-metals will be negatively charged. In covalently bound molecule, however, how do you determine who's going to bear positive charge, who's going to bear negative charge? In the case where you do not have a transferred electron, rather you're sharing an electron. Well, we can assume all of the electrons are being equally shared. Now we know because of the electron activity that's not going to be the case. They're not going to be equally sharing the electrons when you have two different types of atoms with one another. But how do we determine that case? How do we determine the charges on each of the atom in a covalently bound molecule? We use this equation to calculate what we call the formal charge. So Fc formal charge equals to MVE, that's the number of valence electrons, total number of valence electrons, minus the sum of the LP, that's the lone pair electron, plus 1/2 of the bounding electron. Okay, that's what VE stands for. This is an equation that we can use to determine the charges on different atoms in a covalently bound molecule or ion. Now, why is this important? Because you always need to know the electron distribution. Electron distribution determines the chemical reactivity or chemical property of the species there. Now, this is a topic that you do need to pay attention to, especially if you're going to get into organic chemistry. Okay, so the first 2-3 weeks of the discussion in Chem 201, organic chemistry, you'll probably see this term again, formal charge. We need to know, we need to be able to determine the formal charge on the atoms involved in organic molecules there. So the formal charge will actually help us to pick the best Lewis structure. Many of the argument about different types of Lewis structure is based on the formal charge distribution in that particular molecule there. Now there are certain guidelines there, or the rules, if you will, and the sum of all formal charge in the neutral molecule is 0. Very much like ionic compound. The total, the sum of all the charges there, positive and negative, equals to 0. Okay. Now the sum of all formal charges in an ion must equal to the charge of ion. That is also the case for the polyatomic ions there. So the total charges between the two atoms in a polyatomic ion there adds up to the net charge on the ion there. And if you could end up with a smaller or 0 formal charge on an individual atom, and it's better than assigning a higher, a larger charge. Well, higher charge means a greater degree of separation. Well, when you form covalent bound molecules there, we try to get equal sharing, but because of the electron activity, the sharing is not going to be equal. But if you assign formal charges there, And if it's possible to assign a particular atom with a smaller or zero formal charge, well, it's better than having a larger number there. So that's another thing you want to remember there. And when you have to have a formal charge, and this is probably the most important thing that you need to remember. When you have to have a formal charge, then the negative formal charge must be on the most electronegative atom, which only makes sense. How do we define electronegativity? The ability of the atom in the molecule or ion to attract electrons toward itself. So if you have the most electronegative atom there, that means that it has the strongest ability to attract electrons toward itself, and then they should bear the negative charge. So this is something that you do need to remember. Okay, so for the formal charges and calculation involved in formal charge there, again, if I ask you to calculate the formal charge there, I will give you that equation. You don't have to memorize that equation, you just need to know what each term represents. Number of valence electrons. So for example, if we have a chlorate ion, okay, and we have one chlorine and 3 oxygen in there, and say we're going to calculate the formal charge on chlorine. Chlorine is group 7A. So the number of valence electron equals to 7, okay, and LPE, that's a lone pair of electron, okay, and you have one lone pair, so there are 2 electrons in there, and plus 1/2 of the bounding electron, you have 1, 2, 3. 3 single bound. 3 single bound represents 6 electrons. And the reason we divide them by half is because, well, chlorine is only responsible for half of those 6 electrons there. Then you add everything together, then chlorine in this case is going to bear a positive 2 charge. Okay? And then in calculating the oxygen is going to bear a negative charge. Now this is actually one of the exceptions there. And when we were talking about the charges of the nonmetal elements there, we say fluorine, chlorine, bromine are -1, except chlorine, bromine are -1, except when they're combining with oxygen. Oxygen in this case is going to take the negative charge there. So in this case, when you calculate the negative formal charge for oxygen and chlorine, in this case, chlorine ends up with +2. Each oxygen is -1. Okay, and again, 6 here. That's the NV, number of valence electrons. Oxygen group 6A, so you have 6 valence electrons. And if you look at each oxygen, in this case, oxygen has 6 lone pair electrons on it, and plus 1/2 of the bounding electron. There is only one single bound between chlorine and oxygen there. So 1/2 times 2. And you add the numbers together, you end up with -1. Now you do have 3 oxygens in there. So -1, -1, -1, total of -3, +2. -3, +2, you end up with 1 negative charge. So the sum of the formal charge does equal, in this particular case, does equal to the net charge carried by the chlorate ion. So this is how the equation that we use to calculate the formal charge for each of the atoms in the either in the molecule or polyatomic ion there. Okay, and there are more examples in chapter 9 there on page 404 and 405 there. Make sure you, when you're reading the textbook there, make sure you take the time and go through those examples there and trying to figure out, follow the example there and trying to understand how do we calculate formal charge. And I can guarantee you when you get into organic chemistry, this is a topic that you will see again in organic chemistry. Okay, so this would be the end of chapter 9. So we are going to look into more details